Hello everyone, welcome to topic 6.1, endothermic and exothermic processes. By the end of this, you should be able to explain the relationship between experimental observations and energy changes associated with chemical or physical transformations. There are no specific equations for this. This section is, for the most part, conceptual. So many reactions and changes involve either the absorption or release of energy in the form of heat. We describe these as either endothermic, where heat is absorbed, or exothermic, when heat is released. We have to define what we're studying, though, and we use general terms such as system, surroundings, and the universe, where the system is the part of the world that you are studying. This might be a beaker, salt, water, thermometer, or it could just be the salt that is dissolving. Okay, so you have to define what the system is, and that's always the thing that you are studying. You yourself are usually part of the surroundings, which includes everything else around the system. This might be the air, tabletop, hands holding the beaker, or it might be the water in the beaker and the thermometer. And then the salt then would be the system. The universe is both the system and the surroundings together. So what you're studying and everything else makes up the universe. It is important to always define the system and surroundings when you are looking at a problem. Heat, which is given the variable Q, or work, which is given the variable W, is always transferred between the system and the surroundings. Therefore, energy of the system is equal to the negative energy of the surroundings. So what is lost by one is gained by the other. Or if no work is done, then the heat lost is equal to the heat gained. And that is defined by that equation. The quantity or amount of heat is the amount of thermal energy or heat energy transferred from something that is hotter to something that is colder. The units for heat are energy units, which include but are not limited to joules or kilojoules. We will use joules and kilojoules the most in class, though. If thermal energy is transferred from the system to the surroundings, we see that the heat is negative. If thermal energy is transferred from the surroundings to the system, then the heat energy is positive. Work is the energy needed to move something against a force. In chemistry, we generally think about that as as an expanding gas that pushes on a piston. So chemical work is also often thought of as work is equal to negative P times the change in volume. The units for work are atmospheres, ATM, so for pressure, times liters, given here. This is also shown as joules. Okay, so energy units are also used for work because it is an energy, but because it's based off of pressure and changes in volume, it has the liter atmosphere units as well. If the system is pushing on the surroundings and expanding a piston, then we would say that the work is negative because you have an increase in the volume, so pressure and volume are both positive. So work is generally negative then. If the surroundings are pushing on the system and this compresses a piston, then the work would be positive because you have a negative change in volume. It's getting smaller. And there are visuals to the right over here where for heat, when we have energy going in, that's a positive heat shown here. And then when we have that heat leaving, that's negative. So this on the left is endothermic, and then on the right is exothermic. Here, when work is done on the system, we are actually putting energy into the system. So this is our endothermic, and then when we have negative work, that's exothermic, because energy is leaving or the system does work on the surroundings. Okay, so let's look at endothermic and exothermic processes side by side. So here on the left we have an endothermic process where we see heat being absorbed by the system from the surroundings. This means that enthalpy, or delta H, change in enthalpy, is positive. The products then are higher in energy than the reactants. Phase changes, which we're going to look at that graph right here, include melting, boiling, vaporization, and sublimation. So those are all the endothermic phase changes. Additional changes that are endothermic involve the breaking or separation of substances. This includes breaking bonds. So when you dissolve something and like the salt, the ions in a salt come apart, you are pulling them apart. That is an endothermic process. Okay? But the interaction of the salt with water could be severely exothermic, which then means the overall process is exothermic, and we'll look at that more in the future. Below we see a heating curve because the temperature keeps increasing. Okay. Over here on the other side, we have exothermic processes. In this, we see that heat is released from the system to the surroundings. So for endothermic, you would feel this as cold, because your hands are part of the surroundings, and so the system is stealing energy from your hands. So energy is going from your hands into the system you are studying. On the other side, we have our exothermic process, and this is felt as hot or warm. Okay, because the energy is going from the system into your hand and warming your hand, which your hand is part of the surroundings. In this, we see that enthalpy is negative, that the products are lower in energy than the reactants. And the phase changes that are included here include freezing, condensation, and deposition. These, when we form bonds, so anytime we combine materials, formation of bonds is included in that. That is an exothermic process. Energy is released because they are going down to a lower energy state. Okay. And so also a cooling curve is an exothermic curve. So when a solution forms, so we dissolve salts or even sometimes sugars or whatever's dissolving something into water, there are processes that take place by combining all three processes. You can determine if the dissolution overall is an endothermic or an exothermic process. So we have to look at these three, where first the solvent must expand by overcoming its intermolecular forces. That is an endothermic process. You have to put energy in to pull the particles apart. The solute must also expand by overcoming its intermolecular forces. That again is an endothermic process. So pulling things apart, as we saw up here, breaking, separating, is an endothermic process. You have to pull. You have to put energy in to pull them apart. Then finally the solute and solvent recombining, this process, because they are now forming new interactions, they are combining their materials, this is an exothermic. When we look at all three of these together and the total energies, you would see whether or not a process, the full process, is endothermic or exothermic. Each step is one or the other, but based off of how endothermic or exothermic that process is, based off of the strength of the intermolecular forces, that could give you an overall endothermic or exothermic process. Okay, so now we're going to look at some practice problems. Instant coffee is made through a process called freeze drying. First, the coffee is made in the traditional way, and then coffee is cooled until it becomes a solid. Finally, the pressure is decreased and the ice in the coffee changes to a gas, leaving behind the freeze-dried coffee granules. Identify the two phase changes that take place and classify them as endothermic or exothermic. Well, it tells us first the coffee is made a traditional way and then is cooled until it becomes a solid. So coffee, our first one, coffee, oops, two E's, goes from a liquid to a solid, and we call that freezing. Well, you're cooling your system or removing energy from your system when you freeze something, so that is an exothermic process. And so when we are saying our system, coffee is our system, and everything else then would be the surroundings. Finally, so our next one, the pressure is decreased and the ice, so coffee ice, the ice changes to a gas. So ice is a solid and it changes to a gas, and this leaves behind freeze-dried coffee granules. So it's first frozen and then dried by removing the ice. So solid to a gas, that is a process called sublimation. Dry ice, where solid carbon dioxide changes from a solid to a gas, that is sublimation. Okay? Because the particles are spreading apart and moving faster as it goes from a solid to a gas, and the fact that gases are higher in energy than solids, we know that you have to put energy into it, so this would be an endothermic process. Okay, so for our we do, we're going to answer the 3 questions shown here based off of the scenario provided. So a solution of ammonium nitrate was created by dissolving 5.02 grams of ammonium nitrate in 100 milliliters of solution at 22.3 degrees Celsius. After forming the solution, the temperature was 17.3 degrees Celsius. Did heat enter or leave the system? While looking at the overall temperature changes, we see that the overall temperature goes down, so our overall thermal energy has decreased. So we would say that heat has left the system because the temperature decreased. So if heat or energy is leaving the system, that means the sign for Q, or heat, is negative, because the energy is leaving the system. And so is this dissolution process endothermic or exothermic? Well, energy is leaving the system, so it would be exo. Okay, sorry, I had a brain fart, guys. So that concludes section 6.1 notes. After this, use the concepts covered to go through the you do questions, which is pretty short. It's just 3 questions. Check your answers with the answer key online, and thank you for tuning in.